So only I told in one of the previous lecture that mathematics is speaking something to us. We should be able to understanding it. We should understand what my equations are telling me. Okay, the above expression, the integral expression is one such expression which is I have splitted one integration into two. But what each term is telling me is very important. So if we study the electrical subjects, visualizing what the mathematics is speaking to us, then you will appreciate the beauty of electrical science. Here, now the inductor is behaving differently at different conditions. Okay, so let me see. Let me put it in a common representation. Now I have this inductor. Okay, this inductor at t equal to 0 plus. At t equal to 0 plus, so I have this inductor L carrying current IL. Now at t equal to 0 plus, it means just after switching. So at t equal to 0 plus, inductor acts as open circuit. So this is acting as open circuit. Inductor is acting as open circuit. Now as t tends to infinity, it is under steady state condition. So under steady state condition, inductor is acting as short circuit. Okay. The same inductor L is acting like short circuit. So this is with initial condition 0. This is with 0 IL minus. Okay. So I can say no initial current. That is IL of 0 minus is okay. Now if I have an initial current, let IL of 0 minus equals to, I have some initial current, say I naught. Some current is flowing. IL of 0 minus should be a current itself. It cannot be any other parameter, it cannot be any other quantity. It has to be current. Okay. So there is some initial current, say I naught. Then at t equal to 0 plus, or at the time of switching, or during its initial condition, without application of voltage, go back to this circuit, at t equal to 0 minus means what? I haven't closed the switch yet. So before the switch is closed, there is no application of source voltage VDC or source voltage Vs. But still, before t equal to 0, that is for t equal to minus infinity to t equal to 0 minus, okay, this term, there is some current I naught. Okay, what I consider this is now I naught. What does it mean? Without voltage source, there is current flowing in the inductor. It means that inductor is equivalently behaving as a current source. So what I can conclude here is, at the time of switching, okay, or at IL equal to, if IL equal to 0 minus, I have some current I naught, then I can say that at t equal to 0 plus, or during switching, or immediate, just because the condition during switching is the same condition immediately after switching, because current will not change instantaneously. So at t equal to 0 plus is equal to t equal to 0 minus. I have 0 minus. So therefore, the inductor is behaving as a current source across the open circuit. Or if it is confusing, we will take out the open circuit itself. The inductor is behaving as a current source. Don't worry about the direction. It is a current source of value I naught. This is inductance here. Because there is some initial current I naught without application of voltage. So definitely that should be a source. Okay. Now during steady state condition, if there is initial current I naught, during steady state condition, now I know during steady state condition the inductor behaves as short circuit. That will not change. Whether there is initial current or no, the behavior of inductor will not change. The inductor is still behaving as short circuit. But what about this I naught? This I naught is still existing. So the inductor is like a current source across short circuit. A current source across short circuit. So this is the initial condition of an inductor. This is an initial condition of an inductor. So for the review, what I can say is, what I can summarize is, the inductor operates as open circuit at the time of switching, act as short circuit under steady state condition. Okay. The current in inductor does not change instantaneously. That is the reason why the current lags behind voltage if there is change in voltage. Second, if there is some initial current, then the inductor will behave as a current source at the time of switching and a current source across short circuit under steady state condition. So at the time of switching is the transient condition, as t tending to infinity is a steady state condition. So under transient condition, my inductor is behaving as open circuit with no initial condition, and if there is initial condition, the inductor is behaving as a current source. Under steady state, it is behaving as short circuit with no initial current, and it is behaving as a current source across short circuit under steady state condition. So this is the summary of behavior of inductance with respect to time. In the previous subject, fundamentals of electrical science or basic electrical engineering, we have seen how the inductor is behaving for AC, and all those analyses are steady state analysis. Okay, but this is how the inductor behaves with respect to time. Okay, so we have one more energy storage element, capacitor. We shall see. And what happens with inductor, exactly opposite happens with capacitor. If here current is not changing instantaneously, in capacitor voltage will not change instantaneously. That we will prove. Shall see initial condition in capacitor. So I will consider a capacitor of capacitance C connected to a voltage of VDC. There is a switch operating at t equals to 0. There is some voltage developed across capacitor. I will take this as Vc. So I have considered a capacitor of capacitance C connected across a voltage source of VDC, and the voltage charged across capacitor, let me take it as Vc. Okay, there is no change in VDC and Vc because there are no other elements in between. Okay. So if I consider this as the direction of current flow, then this plate will be higher potential, other plate will be at lower potential. The plus sign minus sign across capacitor states higher potential point and lower potential point. That doesn't mean positive charge and negative charge. Okay. Generally in my normal day speaking, I say one plate of the capacitor is charged positively, other is negatively. It doesn't mean that there are neutrons here and there are protons here and there are electrons here. The plus and minus sign in any electrical circuit, in any electrical system, indicate higher potential point and lower potential point. It doesn't mean positive charge and negative charge. Okay, so this what I can say, clarity must be there. Okay. Now, when I apply the voltage, some charge is accumulated across the capacitor. So that charge is given by charge in C is, I can write Q equals to C into V. Q equals to C into Vc, I will take the voltage across capacitor. Vc. Q equal to C into Vc. Now, if I take the rate of charge, okay, the rate of charge is given as dq by dt equals to C dVc by dq by dt equal to C dVc by dt. Now what is dq by dt? It is nothing but the rate of flow of charge or the rate of charge which is given by, so we have dq by dt is current which is equals to, here I will take IC, the capacitor. Take this as IC. Okay, so I can write this expression as IC is equals to, or I will take it as IC of t, because I am doing everything with respect to time. I will take IC of t equals to C dVc by, okay, let us take this as expression 1. This is expression 1. Now, if the voltage applied is a steady voltage or a direct voltage, a DC voltage, then my dVc by dt becomes 0. For steady voltage, steady means DC. For steady voltage Vc, dVc by dt is 0. dVc by dt is equal to 0. Therefore, my IC of t is equals to, my IC of t is equals to 0. So for steady voltage, this is for steady voltage Vc under steady state, dVc by dt is 0. So my IC of t becomes 0. So we know that when current becomes 0, the circuit is equivalently taken as open circuit. So under steady state, the current in the capacitor becomes 0. It means what? Under steady state, the capacitor is behaving as open circuit. That is, under steady state, capacitor act as open circuit. Under steady state, inductor was acting as short circuit. Exactly opposite behavior we get of the capacitor when compared to inductor. So if I understand one element, the second element is complement of that. So inductor and capacitor are always complement to each other. Under steady state, capacitor acts as open circuit. If I have to give the expression for Vc from this equation 1, okay, so from equation 1, I can write dVc is equals to, okay, 1 over C IC of t dt, or I can integrate on both sides and I take Vc is equals to 1 over C integration IC of t dt. Okay, 1 over C integration of IC of t dt. Let me take this as equation 2. Again, I know the capacitor as an energy storage element. So I should be taking into account the previous condition of the capacitor also before I have operated the switch. So therefore, the integral limits will be from the time instant before the switching to the time instant long after the switching. The integral limits okay, are integration minus infinity, exactly the same what we have taken for inductor. So therefore I can write Vc, I will write it as Vc of t only. There is same, because it is IC of t, I can write this as Vc of t. So Vc of t is equals to 1 over C integration minus infinity to t IC of t dt. Okay, minus infinity to t IC of t dt. Now again I can split the integration. Here from as 1 over C minus infinity to 0 minus IC of t dt plus 1 over C integration 0 minus 2t IC of t dt. So the first integral again indicates the history period of the system. Okay, so this indicates the history period. Okay, history period. History period in the sense it is the initial condition. It is the initial condition. So I can write the history period expression, that is, I can write this expression 1 over C minus infinity to 0 minus IC of t dt as Vc of 0 minus the initial condition of the capacitor. Therefore, I can write Vc of t as Vc of t is equals to, I can write Vc of 0 minus plus 1 over C integration 0 minus to t IC of t dt. We have seen what is the condition of the operation of the capacitor at steady state. So capacitor acts as open circuit under steady state condition. I have initial condition Vc of 0 minus. Now I want to know again what is the operation of the capacitor at switching condition. What is the operating of the capacitor at switching condition? Okay. So during switching at t equal to 0 plus or immediately after switching at t equal to 0 plus, what is the capacitor voltage? For t equal to 0 plus. Okay. So what does it mean? Immediately after switching, so for t equal to 0 plus, Vc of 0 plus is equals to Vc of 0 minus plus integration 0 minus to 0 plus IC of t dt. IC of t dt. Again, the switching time is 0. The time of operating the switch is 0. Therefore, time taken to operate the switch is 0. Hence, my second integral become 0. Okay. We can write here as switch operates in 0 time. As switch operates in 0 time. Okay. Integration 0 minus to 0 plus IC of t dt is equal to 0. So therefore I can write here Vc of 0 plus is equals to Vc of 0 minus. Again, this is one of the important deduction. So what does it mean? The voltage across capacitor immediately after the switching is same as the voltage across capacitor just before the switching. Okay, so I can write here voltage across capacitor just immediately after switching is equals to voltage just before switching. So what does it mean? Yes, again what does it mean? Here the voltage across capacitor does not change instantaneously. Voltage across capacitor does not change instantaneously. So this is one of the important statement we have to remember. Again, go back now to the single phase AC. There we have talked about the current. We said current lags behind the voltage in inductor and it leads the voltage in capacitor. But actually in capacitor current is not leading, it is the voltage which is lagging. Because voltage will not change instantaneously in the capacitor. Okay? So here voltage lags behind the current in capacitor. In inductor current lags behind the voltage in an inductor. Okay? So during switching, okay, or in for a capacitor, the voltage will not change instantaneously. Now we will see what is the condition or the state of the capacitor at the time of switching. When this integral is becoming 0, what is this integral? This integral is voltage. This integral is giving me the voltage. See, if LHS is voltage, every term in RHS represents voltage. If LHS is current, every term in RHS represents current. If LHS is power, every term in RHS represents power. Okay, this we should be conscious about. So the second term in this equation is an integral which is representing the voltage. At the time of switching, this integral is becoming 0. It means at the time of switching, the voltage is becoming 0. So when voltage is becoming 0 at the time of switching, the capacitor behaves as short circuit. Okay, so we will see the same thing here. I have an expression for current. IC of t is equals to C dVc by. Now at the time of switching, okay, as switch operates in 0 time, as a switch operates in 0 time, during switching, my dt becomes 0. Therefore, during switching or at t equals to 0 plus, okay, my IC of t is tending to infinity. My IC of t is tending to infinity. When current is infinite and voltage is 0. See, this expression is telling the current is infinity. This integral is telling the voltage is 0 at the time of switching. So both are telling me that at the time of switching, capacitor acts like short circuit. So we can say that at switching, capacitor acts as short circuit. Capacitor acts as short circuit. So if I see the capacitor now, so I have this capacitor with C. Okay. So at t equals to 0 minus, capacitor is acting like open circuit. Capacitor is acting like open circuit. At t equal to 0 plus, during switching, at t equal to 0 plus, capacitor acts as short circuit. This capacitor and this is short circuit. Now under steady state condition, as t tending to infinity, capacitor acts as open circuit. Capacitor acts as open circuit. if there is some initial voltage across capacitor, here no initial voltage, no initial voltage. Now if I have some initial voltage across capacitor, okay, initial voltage say V0, that is Vc of 0 minus is equals to V0. Then the capacitor, now go back to the circuit again. See, statement wise I can directly say, but when we have established so long relations, we will see in detail, okay, why it is so. Now, for t equal to 0 plus, okay, immediately after the switching, okay, or during switching or before the switching. So before switching, the capacitor, before switching means the switch is not yet closed and capacitor is carrying some voltage V0. So without application of any other source, there is some voltage existing, means the capacitor is acting like a voltage source. Okay. So here I can write for t equal to 0, for t equal to 0 plus, capacitor acts like voltage source, of value V0. Voltage source of value V0. Now at steady state condition, capacitor act like voltage source of value same V0 in series with an open circuit. So this is about the analysis of capacitor and inductor with their initial conditions. Okay. So what we have observed in the basic electrical engineering through mathematical expressions using the phasor relations, the same thing we have observed here in a different terms, but concluding the same behavior of the capacitor and inductor. So the inductor is not changing the current instantaneously, it means the current will lag behind the voltage. The current is not changing instantaneously in inductor, but the voltage is changing instantaneously. The moment I apply the voltage changes, gets applied. If I change the value of source voltage, the voltage value across the inductor will change simultaneously at the same instant. So there is instantaneous change in voltage across inductor, but the current in inductor is not changing instantaneously. Therefore, I can say current lags behind voltage by some angle. Thus, complementary is with the capacitor. The voltage in capacitor doesn't change instantaneously, therefore voltage lags behind current in a capacitor. Okay. So with these established relations, in forthcoming classes we will be applying these concepts to see the transients and initial conditions with various variety of circuits and some examples with them. So this is for the day. Thank you for your hearing.